What specific problem does the Infinity Bitwise Visual AutoRegressive Modeling aim to solve regarding existing autoregressive models and diffusion models in text-to-image generation?
The Infinity Bitwise Visual AutoRegressive Modeling aims to address significant limitations in existing autoregressive models, particularly their reliance on index-wise tokens, which lead to quantization errors and loss of fine-grained details in high-resolution images. These models struggle with inferior reconstruction quality and detail compared to diffusion models, primarily due to the inefficiencies of next token prediction and the fuzzy supervision that results in visual distortions. Infinity proposes a novel bitwise modeling framework that replaces index-wise tokens with bitwise tokens, allowing for a dramatically expanded vocabulary size of 2*64, which enhances reconstruction quality and detail representation. Additionally, it incorporates bitwise self-correction to mitigate train-test discrepancies caused by teacher forcing training, enabling the model to correct errors and improve overall image generation quality. Ultimately, Infinity not only improves the scaling and detail representation capabilities of discrete generative models, but also surpasses leading diffusion models in high-quality text-to-image generation.
How does the proposed Infinity methodology work? Illustrate the key algorithmic steps involved in the Bitwise modeling framework, including the Bitwise Visual Tokenizer and the Infinite Vocabulary Classifier.
The proposed Infinity methodology operates through a bitwise modeling framework that enhances image generation quality by utilizing bitwise tokens instead of traditional index-wise tokens. The key algorithmic steps begin with the Bitwise Visual Tokenizer, which encodes images into multi-scale residual maps and quantizes these maps into binary outputs, significantly increasing the vocabulary size to 2*64. This allows for improved reconstruction quality, as evidenced by a reduction in reconstruction loss scores on benchmarks like ImageNet 256. Next, the Infinite Vocabulary Classifier, IVC, replaces conventional classifiers by employing binary classifiers in parallel, predicting whether each residual feature is positive or negative, which drastically reduces computational costs and improves fitting capabilities. Additionally, the framework incorporates bitwise self-correction, where random bit flips simulate prediction errors, allowing the model to re-quantize and correct mistakes, thus addressing train-test discrepancies and enhancing overall image generation quality.
Can you provide a simple yet illustrative example to demonstrate how the bitwise self-correction mechanism functions in the Infinity model?
The bitwise self-correction mechanism in the Infinity model operates by simulating prediction errors during the training process. For instance, when predicting the residuals R_k at a certain scale, the model randomly flips some bits in R_k with a probability sampled from a uniform distribution, creating a modified version R_k_flip that contains intentional errors. This R_k_flip is then used to recompute the input features for the next scale, allowing the model to re-quantize and generate a new target, R_k+1. This process enables the model to recognize and correct mistakes made in earlier predictions, effectively mitigating the train-test discrepancies caused by traditional teacher forcing training. By incorporating this self-correction capability, Infinity enhances its ability to produce high-quality images, as it learns to adjust based on previous errors rather than propagating them.
What specific benefits does the Infinity method offer over traditional autoregressive and diffusion models in terms of efficiency, visual detail representation, and generation quality?
The Infinity method offers significant advantages over traditional autoregressive and diffusion models by enhancing efficiency, visual detail representation, and generation quality. Specifically, Infinity achieves a 2.6 times reduction in inference latency while maintaining the same model size, making it faster than leading diffusion models like SD3.5. In terms of visual detail representation, Infinity employs a bitwise modeling framework that allows for a vocabulary size of 2*64, resulting in reconstruction quality that surpasses previous discrete tokenizers and achieves scores comparable to continuous VAEs. Furthermore, Infinity demonstrates superior generation quality, as evidenced by its performance on benchmarks where it outperforms diffusion models, achieving a GenEval score improvement from 0.62 to 0.73 and a win rate of 66% in human evaluations. Overall, Infinity combines the scaling and speed advantages of autoregressive modeling with the detailed reconstruction capabilities of diffusion models, setting a new standard in text-to-image generation.
How was the Infinity method validated, and what datasets or benchmarks were used to demonstrate its effectiveness in comparison to existing models?
The Infinity method was validated through extensive evaluation on popular text-to-image benchmarks, including GenEval and DPG, where it achieved the highest overall scores, such as 0.73 on GenEval and 83.46 on DPG. Additionally, human preference evaluations were conducted using benchmarks like ImageReward and HPSV2.1, where Infinity consistently outperformed other models, indicating its superior image quality and prompt adherence. The model was also tested on a validation set comprising 40,000 text-image pairs to measure Frechet inception distance, FID, further demonstrating its effectiveness. Qualitative results showcased Infinity's ability to generate high-fidelity images across various categories, adhering closely to user prompts. Overall, these evaluations confirmed Infinity's advancements over leading models, including SDXL and DALL-E3, in both quantitative and qualitative aspects.
What limitations or challenges remain with the Infinity approach, particularly concerning its computational complexity or applicability in other domains?
The Infinity approach, while significantly improving upon previous models, still faces challenges related to computational complexity, particularly with the scaling of the vocabulary size. Although the Bitwise modeling framework allows for a vocabulary size of 2*64, the computational resources required for training and inference can become prohibitive, especially as the model size increases. The use of a Bitwise infinite vocabulary classifier, while efficient, still necessitates careful management of memory and computational costs, particularly when dealing with high-resolution images. Additionally, the reliance on Bitwise self-correction introduces complexity in the training process, as it requires simulating prediction errors and re-quantizing features, which may not be straightforward to implement in other domains outside of text-to-image generation. Lastly, the performance gains observed in specific benchmarks may not universally translate to all types of visual generation tasks, indicating potential limitations in its applicability across diverse domains.